Is it visible to everybody?
Yes, ma'am.
Yes, ma'am.
Okay. So we have seen the design for shear steps. So the content what is included in unit 3 I have just included over here. Modes of cracking, shear transfer mechanism, shear failure modes, what is nominal shear stress, critical section for shear design, shear resistance of RC section, and design of RC section subjected to shear as per Indian Standard Code. All these are the points included in Unit 3, Part 1, out of which the first 4 points we have already discussed in earlier lecture. We have also discussed about shear resistance of RC section, how the entire shear force is resisted by the RC section. That is, some part is resisted by the concrete, some is resisted by aggregate interlocking, then the remaining is resisted by double action of main reinforcement, and finally the remaining will be resisted by the shear reinforcement for which we conduct the shear design. Okay. Today we will see, and we also discuss about the various codal provisions, whatever are the specifications given by Indian Standard Code. Those also we have discussed in Monday's lecture. So all these we have already discussed. I will quickly go ahead and have you noted down all these steps, students?
No, ma'am.
So if not,
Ma'am.
right now we don't have, yes. Okay, right now we don't have a time to write down all this. So I suggest everybody quickly to take a photograph of this screen. Once you finish taking a picture, I will move further. There are 2 more slides. You have to take photos of those slides also.
Done, ma'am.
Okay. So these are the next steps. Take photograph of this slide also.
Done, ma'am.
And this is the last one.
Done.
Okay. Now take down this problem statement. We will start now the numerical example. I will simply read the problem statement. A reinforced RC beam of size 300 mm by 650 mm is reinforced with 4 25 mm diameter bars on tension side at an effective cover of 50 mm. The effective simply supported span of the beam is 6 meter and the beam is subjected to factored UL of 150 kN per meter. Design the shear reinforcement and do suitable curtailment. Two M25 concrete and Fe415 grade steel are used. So the given data is the size, the dimension, overall dimension of the beam is given, width and the overall depth is given. The effective cover is also given, so we can easily calculate effective depth. The reinforcement details are also given. There are 4 25 mm diameter bars on the tension side. So AST, we can do the calculation for AST. Regarding span of the beam, they have directly given the effective span. In the previous lecture, I have explained you how to calculate the effective span for a beam depending upon the type of a beam, whether it is simply supported or cantilever or continuous beam. Depending upon this type, we have to use the appropriate clause given in IS 456 to calculate the effective span. But here in this problem, the effective span of the beam is directly given, which is 6 meter. Then the beam is subjected to factored UDL, that is uniformly distributed load. So the factored load is also given. So there is no question of applying the partial safety factor and converting the working load into factored load. That step is not required. Directly the factored load is given. Grade of concrete and steel is also given. Okay. So for this given data, we have to design the shear reinforcement. Have you noted down this problem statement?
Yes, ma'am.
Okay. So let us start now solution of the problem. Uh, I will open the board now. quickly, let us write down what is the given data. Okay. Let us write down the given data. Width of the beam is given. What is the value?
300.
300 mm.
300.
Then overall depth is given. Value is
650 mm.
650.
650 mm. The effective cover is also given. So we denote it as DC. Okay. Depth of the cover, which is 50 mm. Correct na? 50 value.
Yes, ma'am.
Yes,
And then
ma'am.
effective depth we can calculate. That is the overall depth 650 minus effective cover. So we are getting the effective depth as 600 mm. Okay. Then they have also provided the details of area of the steel. So AST we can directly calculate over here. 4 number of bars are given. And what is the diameter of the bar?
25 mm.
25.
25 mm. So tell me the area.
1963.5.
Okay, mm square. This is about AST. Then they have given the grade of the concrete also. So what is FCK?
25.
25 Newton per mm square. And grade of steel is also given. So what is FY?
415.
415 Newton per mm square. Okay. Now, what is the first step? You look into the steps for design of shear and tell me the first step. Simply anybody can read the first step.
Calculate design shear force.
Correct. We have to calculate the design shear force. Now the load acting on a beam is also given. So I will write down the value of the UDL, which is given as, what is the value? What is the
150
load?
kilonewton per meter.
kilonewton per meter.
Okay, so I will show you the load as WU. U stands for ultimate. So it is 150 kilonewton per meter. And it is also given that the beam is a simply supported beam. So let us draw first the diagram for a beam. So this is a simply supported beam subjected to UDL. Take down the diagram in your notebook also. Show the load 150 kilonewton per meter. The effective span is also given. What is the value of the effective span?
6 meter.
6 meter. Now we have a beam and we have to calculate the ultimate shear force. So quickly let us draw the shear force diagram for this given loading condition. So to find out or to draw the shear force diagram, we will require to calculate first the reactions. So tell me what is the reaction you are getting for this given beam.
450 on both the sides.
Correct. So it is 450 kilonewton at both the supports. Now, how will be the shear force diagram? Whether it is a rectangle or
Triangular. Two triangles.
triangular, correct? So at this end,
Triangular.
there will be the maximum shear. At this end, there, I'm not able to draw the vertical line today. I'll start from this is the 450 maximum value, and at the center I will simply mark a point over here. So from the center it will go linearly. It is not at the center. Okay, so this is the 450 value and this is also the 450 value. Am I right? The shear force diagram.
Yes, ma'am.
Okay. Now, if I go back to the problem statement, they are asking that design the shear reinforcement and do suitable curtailment. So we have to provide a shear reinforcement for the maximum shear force value. We can find out here the maximum shear force value as 450 kilonewton. So for that maximum VU value, I will quickly write down here a VU value. VU is 450 kilonewton. Okay, this is SFT. So for 450 kilonewton maximum shear force, we have to design the shear reinforcement and we have to also provide the suitable curtailment. Are you aware of the concept of curtailment?
No, ma'am.
Okay, anybody from you know the meaning of curtailment?
No, ma'am.
Okay. So curtailment, actually, if you consider the dictionary meaning of this word, curtailment means reducing the some material, or reducing the cost, or reducing the load. Curtailment means reducing. Okay. Now, what we have to curtail here? We have to curtail the shear reinforcement. Basically, why we want to do this? Let us understand that first. Many times in the construction field, as we have already discussed during your initial lectures, when we construct any structure, we have to definitely deal with the money, flow of money, okay? And we have to achieve economy in the design itself. So providing or doing curtailment during the design means you are achieving the economy in the design itself. Okay, not on the actual side that we are okay, we are reducing the material here and we are adjusting with the cost and we are achieving economy. That is the another part, that is at the time of the implementation. But at the time of design also, we have to think about the overall economy which we can achieve, because whatever the design we are providing, accordingly the site engineer has to construct the building. So the economy we can achieve during the design itself. So curtailment means we are actually interested in reducing the amount of shear reinforcement that we have to provide for the beam. Now, whatever the force is acting on a beam, for that force, we have to have designed a shear reinforcement so that our beam will remain safe. That is the first priority. But on the same side, if I want to achieve the economy, we have to consider how the shear force varies across the span of the beam. We have right now drawn the shear force diagram. We can observe here, this is the shear force diagram. So the shear force is maximum near the support. As we go on towards the center, the shear force go on reducing, and again when we move to the another support, the shear force goes on increasing. So whatever is the intensity of shear force at the support, the same is not the same will not be at any particular section when we consider within the span of the beam. For example, suppose if I want to consider, say, this particular section. At this section, obviously the shear force is reduced than whatever is the shear force we are getting at the support. Okay, so whatever the reinforcement we are providing close to the support, the same reinforcement will not be required here in this zone, because the total force acting, shear force acting at this particular section of a beam is lesser than the support value. So we can reduce the shear reinforcement over here at this particular section. Similarly, as we move towards the center of the beam, the shear force successively goes on reducing. So near the center, if you observe, the shear force is zero at a particular point, or it is very minimum. In this region, whatever the shear reinforcement we are providing at the support region, it is not required to provide the same reinforcement near the central portion, because that shear reinforcement is not having that much load to carry. Okay, so reducing the amount of steel as we move towards the center, that is nothing but curtailment in shear reinforcement. Okay, now how to reduce the amount of steel? See, the steel, when we provide in the construction or for any structural component, either we consider its diameter or we consider number of bars. So either you go on reducing the diameter or you go on reducing the number of bars. Okay, in any ways you can achieve the curtailment. Now what will happen if you consider the first case, that is I'm reducing the diameter of the bar. So at the end near the support, suppose I have provided 10 mm diameter bar. As I'm moving towards the center, I'm reducing the diameter of the bar. Say I'm providing at this particular section, I'm providing 8 mm diameter bar. Here I'm providing 6 mm diameter bar. What will happen if you consider the along the length, if the longitudinal section of the beam if you consider, with the reduction in the bar diameter, your effective cover will also go on changing continuously. Okay, as you move from the support to the center of the beam, and that is not a good parameter for the design, that your effective cover is going to change at various sections. Okay, so what is done? Instead of reducing the diameter, we can reduce the number of bars. Okay, how to reduce the number of bars now? Instead of providing the same spacing in the bar, we can go on increasing the spacing between the bars. So automatically the number of bars will go on reducing. So if I want to draw a cross section of a beam over here, suppose this is my beam. This is a longitudinal, not a cross section. This is the longitudinal section of a beam. And let us consider the main reinforcement with some different color. This is my main reinforcement. I'm sorry, I'm not able to draw the straight line, exactly the straight line. Okay, and the stirrups we can show in this fashion. So this is my first vertical stirrup, then the second, then the third, like that. Okay, to have a support to the top stirrup, we have to provide the top reinforcement also. We always provide a minimum reinforcement in the compression zone always. Okay, so these vertical lines which are shown with black color, these are nothing but my stirrups. So right now you can see here I have drawn the vertical lines almost at the same or equal distance. Okay, so I have not considered any curtailment right now here. But if I want to show the curtailment, obviously I have to divide the entire beam into different zones, and then I can go on increasing the spacing between the stirrups. So for the same beam, these are my main reinforcement in the top and bottom zone. Okay, and the stirrups, as the shear force is maximum near the compression, near the support, so I have provided the stirrups like this here. As I'm moving ahead, the shear force is reducing, so I can increase the spacing now successively. See, I have increased the spacing. Further again, as I move to the central portion, I'm again increasing the spacing. So whatever the part, whatever the spacing I have provided from one support to the middle of the beam, the same I have to provide in the second half, that is right hand side part of the beam also. So again I have to reduce the spacing over here, and whatever the spacing I have maintained the left hand side of the beam, the same I have to provide in the right hand side of the beam. So in short, if you consider a longitudinal section of a beam, this beam, I have to divide the entire beam into different zones to achieve the curtailment of the reinforcement. Okay, so somehow I'm not satisfied with this diagram, so I will draw the shear force diagram again here. Okay, this is the...
Ma'am?
Yes?
Ma'am, because the shear resist or shear strength or shear force at the middle, in the middle span, it is less. Therefore, we can reduce the number of stirrups over there, no?
Yes, yes. Yeah, that is nothing but curtailment.
Okay.
The same thing I have discussed right now. Na? So we have to reduce the shear reinforcement. It means I'm increasing the spacing here. So if you consider, see if I'm considering this zone of my beam, this zone of my beam, you can observe the spacing between the two consecutive stirrups, and if I will consider this zone of the beam, you can consider the spacing between the stirrups. So if I will maintain the same spacing here, 2 more bar I need to provide here. So number of bars will be 1, 2, 3, 4, 5 in that case. But if I'm curtailing the reinforcement, now I can provide only 3 bars. Okay, so increasing the spacing between the vertical stirrups as we move towards the center from the support, this is nothing but curtailment. Okay, the curtailment is achieved in different ways in the construction. I am just talking right now about the shear reinforcement. The same concept is used for main reinforcement also. If you are erecting the entire steel structure, then there also when we go for a plated girder, etc., that part you will learn in the second semester. But for plated girder also, by adjusting the thickness of the plates in this fashion, we can achieve the curtailment. Is it clear to everybody, the concept of curtailment?
Yes,
Students?
ma'am.
Yes, ma'am.
Okay. So let us come to the shear force diagram now. I have to curtail the shear reinforcement, and I know what is the shear force distribution over the span of the beam. So I will consider now the half the span of the beam over here. So let us consider this span. Okay, half span means I'm considering only 3 meter span of the beam. And for this 3 meter, again, this 3 meter part of the beam, I'm dividing into 3 equal parts. Okay, it means I'm doing the 3 parts of the beam, 1 meter of each. And for all these 1 meter span, I'm going to design now the shear reinforcement by providing the different spacing. Okay, so let us consider all these parts of the beam with a different zone. I'm considering this as zone 1, this is as zone 2, and this is as zone 3, because in every zone there is a difference in shear force value. In the zone 1 there is a maximum shear force, zone 2 there will be a reduced shear force than zone 1, and zone 3 again the shear force will be reduced as compared to zone 2 and zone 1. Is it clear? So I'm considering division of the entire length of the beam or half the length of the beam into 3 parts, zone 1, zone 2, zone 3. And we will go on designing each zone separately for shear reinforcement. Is it clear to everybody? Any doubts in this?
No, ma'am.
Students?
No, ma'am.
So have you drawn these diagrams in your notebook?
Then not
Yes,
the
ma'am.
down one. Then the down one also we have to draw that curtailment.
Yes, zoning. This diagram you need to draw. This not needed. For your understanding, I have drawn these diagrams. If you wish, you can draw this diagram also for your understanding. This diagram you need to draw in your notebook. Zone, showing the zones in the beam. Just write down one statement below this diagram. Dividing the entire beam in 3 zones for curtailment of shear reinforcement. Write down this statement. I'm repeating the statement. Dividing the entire beam in 3 zones for curtailment of shear reinforcement. Is it over?
Curtailment of
Shear reinforcement. Curtailment of shear reinforcement. Is it over?
Yes, ma'am.
Okay.
Yes, ma'am.
Let us start with the design now. So design, I will simply write down here. Design zone 1. Okay, let us consider the design for zone 1 first. So what is the shear force in this zone? The maximum shear force?
450.
450 kilonewton, correct. Okay, now what is the next step? So
Calculate max allowable shear in concrete. VUC max.
correct. So this is the first step. I will write down step by step. This is the design shear force. Design shear force. Second step, maximum allowable shear in concrete we have to calculate. Okay, so that value is given as VUC max. The formula is tau C max into B into D. Am I right? The formula?
Yes, ma'am.
Yes, ma'am.
Okay. B and D values are already known to us. Now we have to calculate tau C max. So let me open now your code. Again, today I forgot to open the code. Okay, can you tell me the page number?
73.
73. Okay. So page number 73. And table number 20. Correct. Table number 20. So if you look into the table number 20, maximum shear stress tau C max depends upon the grade of the concrete. So what is the grade of the concrete given here in the problem?
25.
M25.
25.
So for M25, tau C max is 3.1. Okay. So let us write down all these values in this formula. So tau C max, or I will just write down here, for M25 grade concrete, tau C max is equal to 3.1. So let us calculate VUC max as 3.1 into B is 300, am I right? Into D value, effective depth value. Tell me the value.
600.
It is 600. So VUC max is
558 into 10 raised to 3 Newton per mm square.
it is a force. Tau C max, unit of tau C max is Newton per mm square, and we have multiplied by BD, so the force will be in kilonewton. Okay, so 558 kilonewton. Now what is the next step?
To calculate shear force resisted by concrete.
Before that, there is one comparison. If I will go to the steps here, okay, we have to calculate the VUC max and we have to compare it with VU. That is the important step in the design. See, when the problems are given directly to find out only to consider the only design of shear reinforcement, then this step you can skip, because obviously the size of the section will be given and the grade of the concrete will be given, so that your VUC max will come lesser than VU always. Okay, but when you design the beam, it is important to follow this step, because you are deciding the size also now when you start the design of the beam. Okay, so this step also we have to check. So VUC max must be less than or equal to VU. So what is our VUC max? It is 558 and our maximum VU is coming as 450. So this value is coming less than VU is equal to 450. So whatever is the dimension given is correct. Okay. Now go to the next step, that is step number 3. What is the step? Next step? स्टुडंट्स
मॅम VU नॉट मॅम VU लेस नाही आहे ना पण तिथे
VU ची व्हॅल्यू 450 आहे ना.
Ma'am, we
हा
used to land 558.
हो ना. Oh, sorry. This should be greater. Sorry, I have written a wrong sign. This is greater than VU. Correct. All right. Now come to the
मॅम
next. Yes.
मॅम मग ग्रेटर आहे तर आपल्याला ते दुसऱ्या कंडिशन मध्ये जावं लागेल ना
हा,
म्हणजे
ऍक्च्युली या कंडिशन मध्ये जायला पाहिजे, पण प्रॉब्लेम स्टेटमेंट मध्ये तुम्हाला बी आणि डी ची व्हॅल्यू दिलेली ऑलरेडी, बरोबर.
येस मॅम.
Yes, ma'am.
That we cannot change.
ओके
मग रिसाईज कधी करायचं?
जेव्हा तुम्ही बीम डिझाईन करता तेव्हा. आता आपण बीम मध्ये फक्त शिअर रेन्फोर्समेंटचं डिझाईन करतोय, राईट. ज्या वेळेला तुम्ही बीम डिझाईन कराल त्यावेळेला हे जे आहे ना, हे जे प्रॉब्लेम स्टेटमेंट आहे त्याच्यामध्ये ही व्हॅल्यू नसणार आहे. हा, म्हणजे ऑल दीज डायमेन्शन्स, द एरिया ऑफ द स्टील, एव्हरीथिंग यू आर गोइंग टू डिसाइड वेन यू विल डिझाईन द बीम. तुम्हाला फक्त लोड माहित असणार आहे. ओके, तो पण दिलेला असेल तर. अदरवाईज लोड कॅल्क्युलेशन सुद्धा आपल्याला करायचं आहे. म्हणजे मी मंडेच्या लेक्चर मध्ये सगळं एक्सप्लेन केलेलं आहे. एक्सप्लेन ऑल द स्टेप्स हाऊ टू लोड इज एस्टिमेट, हाऊ टू लोड कॅल्क्युलेटेड ऑन द बीम. So the load will also not be given, the dimension of the beam will also not be given, the details of the reinforcement are also not given. That is, it means you have to design the beam entirely. Okay, in the design of the beam only the grade of the concrete and grade of the steel will be specified. That's it. Rest all, everything you have to decide. Now, right now we are just concentrated on solving the numerical examples for designing the shear reinforcement for all the given data. Okay, is it clear?
Okay. Yes, ma'am.
So actually I should this is not actually okay, so I should not write down okay over here, or better you skip this step, because this is not correct. Truly speaking, as per the design requirements, this value should be less than VU. Okay, so you just skip this step here. Okay, now let us come to the third step. What is the next step?
Calculate shear force resisted by concrete.
Okay, so shear force resisted by concrete we have to calculate now. What is the formula?
Tau C into BD.
And this is denoted by VUC, right? Shear force resisted by concrete, tau C into BD. What is tau C now?
20.
No, tau C is used to denote which value? Tau C is the design shear strength of the concrete, right? And that value we have to calculate from table 19. So open table 19 from IS code. It is on the same page. 73, table 19, design shear strength of concrete, tau C. Now if you look into the table, the design shear strength tau C depends on the concrete grade as well as percentage steel. So we have to calculate first the percentage steel, and then corresponding to the grade of the concrete, we have to use the appropriate value of tau C. And if suppose whatever the percentage steel are given here, 0.5, 0.75, the exactly same value if you are not getting for your given reinforcement details, suppose the value is coming as say 0.60, then you need to interpolate the value over here. Okay, so let us calculate quickly the percentage steel here. So percentage steel will be given as AST upon BD into 100. So what is the AST value?
One nine six 3.5 mm square.
196
3.5.
3.5 into 100 divided by 300 into 600. So percentage steel is
1.09.
1.0.
can you tell me again?
1.09.
Okay, 1.09. So let us consider it as say 1.1 for sake of simplicity. And let us check whether the value corresponding to 1.1 is present here. No, it is not present in this table. So you need to interpolate the value between 1 and 1.25. Okay, interpolate the value between 1 and 1.25. So just do the interpolation and tell me the tau c value. Is the another value 1, 1.25. For 1 and M25 grade 0.64 and 0.70. Just a moment. 0.64 and 0.70. So your tau c value should be between these two values. Yes, what is the value you're getting?
0.62.
Check the value again.
Ma'am, 0.664.
0.664
664.
is the correct value. Okay, this is a design shear strength. So it is in Newton per mm square. Check everybody your values. Okay, so what we have to calculate now? VUC tau c into BD. Just put the values here. So it is VUC is equal to tau c is 0.664 into B into D. Tell me the value of VUC.
One 119.52.
Correct. 119.52 kilonewton. Okay. Now, what is the next step?
Shear to be resisted by shear reinforcement.
Correct. Shear to be resisted by shear reinforcement. Okay. So what is the formula?
VUS is equal to VU minus VUC.
VUS is equal to VU minus VUC. Okay. So VU, we have the value of 450 kilonewton minus VUC, just now we have calculated, it is 119.52. So tell me the VUS value.
330.48.
Correct. Next step.
Shear force to be resisted by minimum shear reinforcement.
Shear force to be resisted by minimum shear reinforcement. Okay. So what is the formula?
VUS V minimum is equal to 0.40 into BD.
0.40
into BD.
Okay. 0.4 BD. So it is 0.4, B is 300 and D is 600. Tell me the value.
720.
7
20.
into something should be there, na?
Ma'am, into 10 to the power 2.
So it is 7,000 Newton.
Yes, ma'am.
So this is 72 kilonewton. Okay. Now the next step. This is VUSV minimum. Next step.
Calculate,
Sorry. Tell me again.
calculate shear force resisted by bent up bars.
Okay. Shear force resisted by bent up bars. Okay. Now let us understand first the concept of bent up bars. If I will go back to this diagram of the beam, whatever we have drawn here. Okay, so blue color line is showing the main reinforcement in the tension zone, and in the problem statement it is clearly mentioned that there are 4 bars. Okay, it means this is the first, then behind that there will be second, then third and fourth, and all these bars, it is not mentioned that there are bent up bars in the section. Now what is the meaning of bent up bars? Bent up bar means, if I will redraw this diagram, same diagram again here, to show you the bent up bars. In the practice, in the beam and also in the slabs, alternate bars are bent. Okay, so if this is my beam, and this is the first bar, the second bar I will show by a green color, which will be exactly on the side of the blue bar. So I will repeat the line here over, but the second bar is bent. So the bent up bars, they look like this. Okay, so the some portion of the bar is bent and it is provided in the compression zone. So if I want to draw the diagram again, the bent up bar will be like this. Okay, so this is my second bar which is bent up. Now this angle of bent is normally practically provided 45 degree. Okay, then my third bar will be also a horizontal one, and the fourth bar will also be bent up, which will be exactly behind this green color bar. Is it clear? The concept of bent up bar. Now in the problem statement, the bent up bar details are not provided, so we can consider that the bars are not bent up here. So I will simply write down what is the notation used to show the shear force resisted by bent up bars. It is VUSB. Okay, this will be 0 as no bent up bars. Now when you design the beam, you have to specify whether you are providing a bent up bars or not. Practically, we definitely provide the bent up bars. Alternate bars are bent up. Suppose only 2 bars are provided in a beam, then we do not provide the bent up bars. But if 4 bars are there, then alternate bars are bent up. Only 3 bars are there, in that case also we do not go for bent up bars. Okay, but for slabs, we definitely provide the bent up bars. Okay. So VUSB will be 0 as there are no bent up bars. Now, what is the next step? We have to calculate the total shear force which is resisted by the concrete, the shear force resisted by minimum shear reinforcement, and shear force resisted by the bent up bars. Okay. So let us calculate VUC, that is the shear force resisted by concrete, plus VUSV minimum, shear force resisted by minimum shear reinforcement, and VUSB, the shear force resisted by bent up bars. So quickly tell me the values. What is VUC?
119.52.
Yes. Plus VUSV minimum?
72.
22.
Plus this is 0. So what is the value?
191.52.
Okay. Now we have to compare this value with the total shear force acting on a beam. If this force is, I will go back to the design steps now. If this shear force, this total shear force, where I have written? Oh, okay, here. This shear force, if it is coming greater than the actual force, shear force acting on a beam, we need not to design the shear reinforcement. We have to provide only the minimum shear reinforcement, that is which we have already calculated here, that is VUSV minimum. Okay, so for this shear force, we have to provide the reinforcement. If this addition is coming greater than VU, if it is coming less than VU, it means the shear resistance provided by concrete by minimum reinforcement and bent up bars are not there. This is not sufficient to resist the total shear force acting on a beam. In that case, we need to provide the design shear reinforcement. Okay, so what is our case now? Let us compare this value with the VU. Yes.
Smaller than का greater than देने का मतलब क्या था?
See here. If this total shear force resisted by the concrete, the minimum reinforcement and bent up bar, if it is coming greater than the total shear force, म्हणजे जे काय आपण कॉन्क्रीट प्रोव्हाइड केलेलं आहे, जे काय मिनिमम शिअर रेन्फोर्समेंट आहे आणि जो काय शिअर फोर्स बेंटअप बार रेजिस्ट करतायत, तो सगळा टोटल फोर्स हा जर ऍक्च्युअल शिअर फोर्स पेक्षा मोठा असेल तर वेगळं शिअर रेन्फोर्समेंटचं डिझाईन प्रोव्हाइड करायची गरज नसते. इज इट क्लिअर टू यू नाउ?
Yes, ma'am.
Now if the shear resistance provided by the concrete, the minimum reinforcement and the bent up bar, if it is coming less than the actual force, it means there is some additional force which we have to resist by additional shear reinforcement. In that case, we need to design the shear reinforcement. Is it clear?
Yes, ma'am.
So what is the case? In our case, what is the value of VU?
450.
It is 450 kilonewton, and this value is coming less than 450. It means provide design shear reinforcement. Okay, we have to provide the design shear reinforcement. Now, for how much force we have to design? Obviously, this is already present there because of whatever the concrete we are providing in the beam, whatever the tensile reinforcement we are providing in the beam. Because of that, this force will get resisted by the beam itself. Whatever is the actual force minus this force, for that remaining force now we have to design or we have to provide the additional shear reinforcement in the form of the stirrups. So let us calculate that force. It is denoted as VUSV, that is the force resisted, shear force resisted by the shear reinforcement, which will be VUS, that is the total shear force to be resisted by the shear reinforcement minus your VUSB, that is the bent up bar. Now VUS, this value we have already calculated over here. What is that value? It is 330. Okay, how we have obtained? We have already deducted the force, shear force resisted by the concrete from the total shear reinforcement. So this is VUS, which is the shear force resisted by the shear reinforcement, which is 330.48. So let us use that, 330.48 minus the shear force resisted by bent up bar, which is 0 here because there are no bent up bar. So VUSV is coming as 330.48 kilonewton, for which now we have to provide the additional shear reinforcement. Okay. Now when we provide the additional shear reinforcement, we assume some diameter of these stirrups, and normally we provide a two-legged stirrups. So what is the meaning of two legs? So if this is the cross section of your beam and these are the main reinforcement. In our case, there are 4 reinforcing bars. So I have drawn 4 circles over here, and some minimum reinforcement in compression zone also we provide. Normally it is two bars. So the shear reinforcement will be like this. It is like this. Okay, and this one end is going here and another going here, which actually provides the interlocking between the stirrups. Okay, so this is actually a frame of steel bar which we are forming. This entire frame is called as stirrup, vertical stirrup, which is specifically used for your shear reinforcement. And if you consider there are 2 faces and there are 2 bars, so it is called as two-legged stirrups. Two-legged stirrups. Is it clear to everybody now? Stirrups means what? And this is nothing but your shear reinforcement. Now we have to design or decide how many such frames of the reinforcement we have to provide throughout the entire beam. It means we are designing for shear reinforcement. Is it clear?
Yes, ma'am.
Yes, ma'am.
Okay. So normally in practice we provide the diameter of these bars as 10 mm and we start with the two-legged stirrups. Suppose 4 reinforcing bars are there in the compression zone also, and you are designing a doubly reinforced section. In that case, 2 additional reinforcing bars will also be there. So I will simply draw that also here. So these are the 2 additional reinforcing bars are provided in the compression zone. In that case, 1 more additional stirrup is provided in this fashion. Okay. I need to use scale here now. Okay, so this is the additional stirrup which is provided, and in this case the stirrups provided are called as 4-legged stirrups. So this is the first leg of red color and the blue color will be the second. So this is called as 4-legged stirrups. Now in our case it is not needed because only 4 reinforcing bars are provided in the tension zone and minimum reinforcement is given in the compression zone, and we are actually designing the singly reinforced section. So for singly reinforced section, normally we go for 2-legged stirrups. So let us write down here now. Providing, I'll write down here. Providing 10 mm diameter. Now this notation for indicating diameter used is different than the notation, this notation, which we use to indicate the diameter of the main reinforcement. Okay, this is purposely done. These notations are used purposely so that all the details when we put on our sheet, there should be the differences between the diameters of the bars which are used for different purposes. The diameter indicated by using this sign, it is normally used to indicate the flexural steel, that is a steel which mainly take part in resisting the movement, and this to indicate the shear reinforcement. So the reinforcement which mainly take part in resisting the shear force. Okay, So this is 10 mm diameter, two-legged stirrups. Okay, so let us calculate now the area of these stirrups, which is denoted by ASV, is equal to, again, the area of cross-sectional area will be pi by 4d square. D here we have assumed as 10 mm, multiplied by, we have considered two legs here. So here, if I will cut the beam here horizontally, I am getting 2 bars. So I have to write down the number of legs here, 2 legs. So what is the ASV value we are getting? Tell me the value.
157.07.
Pardon, please.
157.
Huh?
0.07.
0.07 mm square. Okay, this is ASV, area of the shear reinforcement or area of the stirrups. Now we have to calculate the spacing between the stirrups also. So let us use the formula for spacing. What is the formula for spacing? It is denoted by SV. So if I will go back to your code, the code provides the formula of SV, spacing of the stirrups. It is somewhere here. Where it is, page number 73. Okay. Yes, this formula. We are designing for vertical stirrups, so we have to use this formula. Okay. The same formula is written in your PPTs also, 0.87 FY ASV divided by VUSV into D. Okay. So what is done? This SV we have shifted here. So 0.87 FY ASV into D divided by VUSV, because we want to find out the shear spacing between the stirrups. Okay. So let me write down this formula. SV is equal to 0.87 into Fy into ASV into D divided by VUSV. Okay, let us put now all these values here. 0.87 Fy, 0.87 Fy is 415 into ASV is 157.07 into D is 600 divided by, what is the VUSV value?
330.48.
330.48. This value is in kilonewton. Okay, 415, this value is in Newton per mm square. All these values from the numerator are in mm. So this also I have to consider in Newton. Okay, this is in Newton per mm square. That's why I'm writing this as in Newton. So multiplied by 10 raised to 6. So tell me SV now.
102.95.
0.102.
0.102? You must have not considered in 10 raised to 6 in the denominator.
Yes, ma'am.
Sorry. This must be 10 raised to 3. Sorry. This is in kilonewton. I have to convert it into Newton. So 10 raised to 3. Sorry.
In 102.95.
102.95 mm. This is the spacing between the stirrups. Now there is a limitation for this spacing as per the code. What are those limitations? So the clause number 26.5.15, page number 47, we have to refer. The criteria for spacing between stirrups is lesser of 0.75 D or 300 mm. Okay, so I will go to the clause again, page number 47. We are continuing the lecture for next 1 hour. Page number 47. Okay. Where is the criteria? Page number 47. The criteria is here. Maximum spacing for shear reinforcement. The maximum spacing of shear reinforcement measured along the axis of the member shall not exceed 0.075 for 0.075 D for vertical stirrups and D for inclined stirrups at 45 degree, where D is the effective depth of the section. So this is the first criteria. And second criteria under consideration, in no case shall the spacing exceed 300 mm. So the limitation is SV value should be less than first 0.75 D and second 300 mm, whichever is less. Okay, so let us calculate this value 0.75 into D. What is D?
450.
D is 600. It is 450. Okay, so out of 450 and 300 mm, 300 mm is the least value. So SV should be less than 300 mm, and this is the value which we are getting from the formula. Okay, so just write down one statement. SV we can provide as say 100 mm. Now why 100? Why not 102? Because after the calculation we are getting 102.95. So let us consider as 103 mm. Round it off to the higher side. See, if you go to round it off to the higher side, the spacing whatever is required, we are actually providing a little bit more spacing than the required. If you provide a spacing lesser than the required one, it will be always on the conservative side. In other words, if you provide the spacing little lesser than whatever is required, you are providing the stirrups closely spaced, which will make your design more safe. Okay, so not always when you round off the value for the spacing between the stirrups, round it off to the lower side and not to the higher side. You can consider 102 value also, but practically just think that the laborers are putting these reinforcement on the site and measuring 102 exactly 102 mm, it becomes difficult. So we can reduce the value further to 100 mm, completely rounded off value. Okay, so let us provide the spacing between the stirrups as 100 mm. Okay, so write down one statement now. Here we have actually completed the design for shear reinforcement. We have calculated the area required and we have also calculated the spacing between the stirrups. For zone 1 only, we have to design for remaining 2 zones also. So just write down one statement. Provide 10 mm diameter, 2-legged stirrups at 100 mm center to center spacing in zone 1. We have completed the design for shear reinforcement in zone 1 only. We have to design same for zone 2. So we have to repeat all these steps again for zone 2, considering the corresponding shear force of zone 2. So if I will go back to the original diagram, this is my diagram. Okay, we have just now completed the design for this zone only, zone 1. We have to design for zone 2 also. Okay, so let us complete this zone 2 design also. I will erase now this entire sheet. I will consider the new sheet. Anybody wants to see the design steps? of all these calculation? Any particular step do you want to see again, guys?
येस मॅम स्क्रीनशॉट काढतो एक मिनिट.
स्क्रीनशॉट कसा बसेल याचा? खूपच जास्त लिहिलेलं आहे आणि कसं बसेल एका ह्याच्यात? नॉट पॉसिबल.
नाही मॅम ते काय दिसतच नाही आहे, पण ठीक आहे जाऊ दे.
हा, see, I'm going to provide this video
रेकॉर्डिंग
also.
टाकून द्या ना.
Yes,
हा,
yes, I'm
no problem.
going to provide the video, so don't worry about that. And the steps are with you, so you have to follow the same steps again. What will be the difference? That the shear force acting in second zone is different. Okay, okay. So instead of better to erase, otherwise it will take time, it will consume. I'm going to erase the entire board. Okay. And I will draw the diagram again here. For the beam. This is the load. (150 kilonewton). Okay, the reactions we have already calculated, 450 kilonewton at both the supports, and we had drawn the shear force diagram. And we have divided this half part into 3 different zones, zone 1, 2 and 3. Okay, each of length 1 meter. Okay, the maximum shear force at support is 450. I want now the shear force value at this point. So I will write down that with different colors so that you will understand the value. Tell me the shear force value for at this section, that is 1 meter from your left hand support. What is the shear
300.
force? Correct. So it will be 450 minus 150 into 1, it will be 300. Similarly, tell me what is the shear force at zone 3?
150.
150. Okay. So at zone 3, the value of shear force is 150. Now, let us consider the design of zone 2. Repeat all the steps. The first step, VU we have already calculated, which is 300 kilonewton. Second step, guys.
VUC max.
Yes. VUC max, the formula is tau C max into BD. BD, tau C max, everything is same, right? So the value will remain same. So what is the earlier?
558.
Correct. 558 kilonewton. Third step.
VUC.
VUC, right. VUC is the shear force resisted by the concrete. The formula is
Tau C into BD.
tau C into BD. That tau C depends on percentage of steel. So percentage of steel is constant. The concrete characteristic strength, FCK, is also constant, grade of concrete. So this value will also remain constant. So what is the value we have calculated earlier?
9.52.
119.52 kilonewton. Okay. Fourth step.
VUS.
VUS, the shear force resisted by the shear reinforcement. Formula is VU minus VUC here the value will change because our VU value is different now. So it is 300 minus 119.52. Tell me the value.
180.48.
180.48 kilonewton. Okay. Now the next step, shear force resisted by minimum shear reinforcement, right? VUSV minimum. The formula is 0.4 BD. Okay. So nothing is going to change as per the zone 1. So the value, whatever we have calculated in zone 1, it will remain same.
72.
72 kilonewton. Okay. Now, fifth step.
VUSB.
VUSB. SB.
VUSB, that is the shear force resisted by bent up bar. It will be also 0 because there are no bent up bars. Right?
Yes, ma'am.
Seventh step.
VUC plus VUSV minimum plus VUSB.
Same.
What is this value?
Ma'am, 191.52.
Same value. Okay.
Yeah, ma'am.
Compare this with the VU now. The VU acting in this zone is 300 and this is coming less than VU, which is equal to 300 mm. 300 kilonewton, sorry. Okay. So what is the meaning of this?
We have to provide
Design.
Correct. So providing design shear reinforcement so we have to calculate the VUSV value, which is equal to VUS
0.48.
VUSB. VUSB is 0. Yes, so it is 180.48 kilonewton. So for this VUSV, we have to design for shear reinforcement. Again, whatever the diameter of the shear reinforcement we have considered for zone 1, same we will use here. We will not reduce the diameter, but for that, whatever is the corresponding shear force and whatever is the area of the reinforcement, shear reinforcement, depending upon that, your spacing will change because the VOSV value is lesser now as compared to zone 1. What was the VOSV value for zone 1? You just tell me that value.
330.48.
Correct, 330.48, and now the value is much reduced. It is reduced to 180.48. So obviously your spacing will be increased. Spacing will be increased, and when the spacing will increase, the number of bars will automatically reduce. Okay, so just write down the same statement. Providing 10 mm diameter two-legged bars or two-legged stirrups. Okay, so ASV, that is the area of shear reinforcement, it will remain same as per the earlier one. So just tell me the direct value.
157.0 cm.
Correct. Now let us calculate the spacing. SV is equal to 0.87 FY. I am directly putting the values into ASV is 157.07 into depth is 600 divided by VOSV is 180.48. So tell me the SV value.
188.53.
188.53 mm. Compare this with, this should be less than 0.75 D and second 300 mm. So out of this we already calculated that this value is coming less. So this is SV is coming less than 300 So whatever the value calculated, 188 we can provide as it is, or we can reduce the value or round it off to the lower side. I am rounding it off to say 185 mm. Okay, so just write down provide 10 mm diameter two-legged stirrups handwriting is getting worse now at 185 mm spacing, center to center spacing in zone 2. Okay, so design for zone 2 is also over. Now we will move to zone 3. Okay, now coming back to the diagram. For zone 3, the shear force is 150 kilonewton, which we already calculated. Okay, so let us use that value here. Vu is 150 kilonewton. Okay, so now I think from step number 1 to step number 6, where there will be the change?
Step 4.
Yes, the shear force resisted by shear reinforcement. So let us go to all the steps quickly. This is the shear force. Second is, tell me the values, fatafat. VUC max.
558 kilonewton.
Third, VUC.
119.52.
Fourth value will be changed now. That is VU.
30.48.
VUS, right?
Yes,
It is
30.48.
VU minus VUC. 30.48. See the value, it is very less value, as compared to the zone 1 value. Okay, now fifth, VUS
VUSB minimum. 72.
It will remain same, correct.
VUSB 0.
Correct.
Mama.
Seventh, addition of all VUC plus VUSB minimum plus VUSB. What is the value you are getting? It is the same one, 191.52 kilonewton. Now compare this value with your VU value. Your VU is 150 for zone 3. So this value is coming greater than VU. Okay, it means whatever is the shear resistance shown by the concrete, the minimum reinforcement and bent up bar is not there. So by concrete and minimum reinforcement is sufficient to resist the total external shear force acting on the beam in zone 3. So there is no need to design the shear reinforcement. Write down, provide minimum shear reinforcement. Minimum shear reinforcement. So again, we will provide the same diameter, providing 10 mm diameter two-legged stirrups. So ASV will remain same, which is 157.07. Am I right? The value of ASV. Correct, na?
Yes, ma'am.
Yes, ma'am.
So find out SV. Now we have to calculate the minimum shear reinforcement corresponding to the minimum shear resisted by this. That is for this value, right? This is the minimum shear reinforcement. So I must write down one step here. So in this case, my VUSV will be equal to VUSV minimum, that is equal to 72 kilonewton. So let us use the formula of SV again. It is 0.87, Fy is 415, into ASV is 157.07, into D is 600, divided by VUSV is this value now, 72 into 10 raised to 3. So
472.58.
472.58 mm. Now again compare this value with the conditions. SV should be less than 0.75 D, that value we have calculated as 450 mm, or second is 300 mm, whichever is less. Okay, so this we have selected. So SV should be less than 300 mm, and our calculated value is coming as 472. So provide SV is equal to 300 mm. Is it clear to everybody? The calculated value is out of the limitation. The limitation is SV should be less than 300, or it should not exceed 300 mm. So we have provided SV equal to 300 mm. Okay, so just write down one statement here again. Provide 10 mm diameter, two-legged stirrups at 300 mm center to center spacing in zone 3. Okay, so at the end you are expected to draw the diagram of a beam showing all the details. So let us draw the diagram of a beam. So I am showing half part of the beam only, because the zoning is done for half part. In the remaining half, that is to the right hand side, the zone is same. Okay, so I will simply show the main reinforcement with blue color. Let us hope I will draw a horizontal line here. Okay. And in the compression zone also, now the stirrups I am drawing with red color, so that you will understand easily. Before drawing the stirrups, I have to show or mention here the zones. Okay, so let us consider the three zones here first. This is zone 1. This is zone 2. Okay, and then the zone 3. So when you draw the diagram, when you show the stirrups, the spacing for this zone must get reflected. Okay, so I will draw the first line here, a vertical line. At the end of first zone first. Okay, this is my zone 1, and I'm drawing the vertical stirrups here like this. Please make use of scale when you draw the diagrams. Now, using a tablet, it is difficult to use a scale here. So for this zone, I am providing 10 mm diameter, two-legged at, what is the spacing? It is 100 center to center. Am I right?
Yes, ma'am.
Okay.
Yes, ma'am.
Okay. Now,
Yes, ma'am.
in the second zone, I have to write down in this zone. So before that, I will draw the stirrups also here. Now, whatever the spacing you have shown here approximately, a little bit increased spacing you have to show, because the spacing for zone 2 we have calculated is 180 mm, right? So little bit at a larger distance. So this is again 10 mm diameter, two-legged, center to center, 180 mm. 180 mm center to center.
Ma'am, 185.
Okay, 185. Yeah, it is 185, correct. And the third zone, in which we have provided the minimum reinforcement. So I will draw, the spacing should be larger than this one. Okay, so this is the spacing. Okay, I could show only the two legs here. So this is for zone 3, 10 mm diameter, two-legged, and the spacing was 300 mm, right? 300 mm center to center.
Ma'am,
Yes.
this figure which you have drawn now, is it necessary to draw in exam, or is it
Yes, yes.
understanding?
No. You are expected to draw this diagram in the examination also.
Okay, ma'am.
Because looking at this single diagram, I can understand easily that you have already considered the curtailment. You have considered different zones. You also need to mention the length of these zones. So this is 1 meter. This is also 1 meter, and this is also 1 meter. So entire 3 meter you have divided into 3 zones. And the details of the reinforcement also, that you have provided 10 mm diameter, two-legged, and the spacing. Okay, so the diagram is important. And on your sheets, when you draw the sheets for your term work, the sheets will show all these details. So this is actually the what I can say, this is a practice for you, that when you finish any design, you are expected to draw the diagram. Is it clear to everybody?
Yes, ma'am.
Yes, ma'am.
So
Yes, ma'am.
I will go to the second problem. I know that it's almost 1 now. I will give you the second problem statement. It is very simple. Solve problem number 1, considering 2 bars are bent up. So out of 4, 2 bars are bent up. So whatever the VUSB value we have calculated, that will be not 0 now. In our first problem statement, we have considered as 0, considering no bar bent up. Now, the same problem we have to solve by considering 2 bars bent up. Okay, so if possible, you can try this as a homework. Otherwise, we will solve the same problem in the next lecture. Or shall we start today only?
Ma'am, what will be the angle?
The next section, we will try.
Shall we finish the initial concept of zoning, so that once you come to know what is zone 1 and how the bars are bent up and how the changes will be there in the calculation, I hope you will be able to solve the remaining part at home.
Okay,
Shall we
ma'am.
consider this?
Yes, ma'am.
Yes, ma'am.
All right. So let us move now. I'm again going to clear the entire canvas here. And let us draw the diagram now. Okay. So I will again draw the diagram for a beam. This is the simply supported beam. Loading is also same. So the reactions I'm directly writing here 450. And I will draw now the shear force diagram. Make help of these grids now. Okay, now in this entire diagram, we have to consider the zones. Now, as it is mentioned in the problem statement that two bars are bent up. Now, the bar bent ups are normally done at a spacing of, just write down one statement. Bars are bent up at a spacing of L by 7 or at a distance of L by 7 from support. So from this support at a distance of L by 7, if this is my L by 7, at this distance the bar will be bent. Okay, so obviously we have to consider the zoning accordingly now. No, we cannot consider the zones simply dividing 3-meter half span beam into 3 parts. Okay, because in this region the bars are bent. It means whatever is the tension zone, the total number of 4 bars was there. Out of the 4, the 2 bars are bent. So they are bent and moved in the top region. So in the tension zone, near this portion of L by 7 length, only 2 bars are available. So your AST calculation will change now. In this zone, your AST will be simply 50% because out of 4, 2 bars are present in the tension zone, the remaining 2 are in compression zone. So AST for the support region or for this L by 7 length, it will be different than whatever we have calculated in the first problem. Okay, and this is a specification again given in special practice handbooks which are called as detailing SP34. If you refer, all these dimensions or distances will be given, even in IS code also given. So I will show you later on L by 7 distance. Okay, so what is this L by 7 I'm getting here? L by 7. It is 6 by 7. What is the value?
0.857.
85. Okay. So instead of 0.85, I will consider 8 for my first zone. Okay. So approximately at 0.8 meter, I'm considering my first zone. Now in the remaining, what is the remaining length? 3 minus 0.85. 0.8, sorry.
2.2.
2.2. So I will consider again the 1 meter out of this as zone 2. So this is 1 meter. and the remaining 1.2 I'm considering as zone 3. Okay, you can simply divide the remaining part into two equal parts. 2.2 divided by 2, you will get 1.1, 1.1. So instead of that, I have considered 1 in zone 2 and 1.2 in zone 3. You can consider 1.1, 1.1 also. Is it clear how we have done the zoning in this case? Because the bars are bent, so the bending of bars is done normally at a distance of L by 7 from the support as per the specification. So that I have considered zone 1, and the remaining 2 I have considered or divided equally by adjusting the distances. Now what is the change here? I have to consider the AST calculation near the support, because two bars are bent. So it will be 2 into pi by 4 into d square. 25 mm was the diameter. So tell me this value. AST at support and AST at midspan. So this is AST at support, means AST for zone 1 I have to consider. Okay. And then AST at midspan. At the midspan, all the 4 reinforcement will be present, because bar bending is done at a distance of L by 7 only. So if I will consider a longitudinal section of a beam, this is my entire beam of 6 meter. Okay. So at a distance of 0.8, my bars are bent like this. Okay. For 0.8 distance. And for this remaining portion, that is for midspan, all the 4 bars are present in the tension zone. Okay. So for AST at midspan will remain as it is. So I will simply write down AST at midspan. It is 4 into pi by 4 d square. Okay.
The first one is 981.74.
Sorry, tell me again.
981.74.
981.74 mm.
And
Okay.
second, 1963.
1963.5 mm. Okay. Okay. So this AST we will be using for zone 2 and zone 3. Okay. Now as the AST is changing, your percentage steel will also change. So just quickly I will write down here what is the percentage steel for support. It will be AST upon BD into 100. Okay, 100 into AST upon BD. So what is the value?
.54.
0.54. And this percentage steel will remain as it is, whatever we have calculated for the first problem, which was coming as 1.1, am I right? 1.1%. And this is
PT म्हणजे काय असतं?
हा? काय काय?
पर्सेंटेज ऑफ टी म्हणजे स्केल का?
हा, T म्हणजे स्टील.
आणि पी लिहायचं असतं लाईन दिली तरी पी
PT हे नोटेशन वापरतं पर्सेंटेज स्टील दाखवायला, लिहायला.
ओके.
Okay, is it clear? So we have decided the zones, and now we have calculated the changed value of AST also for midspan and support region. So for zone 1, zone 2 and 3, AST calculation, percentage steel calculation is with you now. So the remaining steps, I think you can follow easily at home. All of you are requested to complete this problem at home. so that in the next lecture I can go to the next type of problem, because one more type of problem is there based on the shear design. Once we finish that, then we can start quickly the design of beams part. Okay. And today is 9th of September. By end of September, we have to finish all the 3 units. So we have completed now third unit half part, second unit half part. So once we start the design of beam in next week, we will finish the second unit also completely, and the remaining part we can finish in time, because you have the mid-semester examination in October. The tentative date is 12th October. Is it clear,
Okay.
everybody?
Yes, ma'am.
So,
Ma'am,
yes,
what is the angle at which the bars are bent up?
45 degree. This angle
Okay.
is always taken as 45 degree.
Okay.
Time to give attendance. We'll stop today's lecture. Give me the attendance on the link provided.